Welcome to the last session before lunch. I'd like to introduce Julie Michelman, hopefully I said that right, talking about Pandas, pipelines, and custom transformers. And once again, for this session for the live stream, if you want to submit questions to Twitter, please tweet at PyData Seattle, and we will ask the questions of Julie as we go. So take it away.
Thank you. So I'm Julie Michelman. I'm a data scientist at Zulily, and I'm here to talk to you about Pandas, pipelines, and custom transformers. So let's jump in with a little background. The Pandas data frame. This Pandas data frame is the sort of core data structure in Pandas. It's a two-dimensional table, and it has labeled rows and columns. Each of the columns can be a different type, which is really nice. So we can have a date column, a numeric, a string column, all in the same data frame. In contrast, NumPy arrays require all of the entries be of the same type. The rows are labeled with an index. This defaults to just the row numbers, but you can also use more complex indices. So for this talk, I picked out a public data set. Special events permits from the city of Seattle. So the city of Seattle has this open data portal where they make a whole variety of data sets open to the public, easy to download, descriptions, and you should check this out if you want to play around with some local data. This data set in particular is applications received and special events permits issued by the Special Events Office of Economic Development since 2014. So anytime there's some big special event that they need permission from the city to hold, the organization will submit an application, and hopefully they get it. The data set was several years long, so I filtered to just 2016, and I cleaned up the row names to lowercase with underscores. So let's take a look. We have this Pandas data frame will import with the CSV function and use head to take a look at the first few rows. There's the application date. Permit status looks like the first few were all complete. Permit type looks like the first few were all special events. The category could be athletic, commercial, community, and there are a few more. The event subcategory, well, here we've run into some null values. It looks like maybe only the athletic events have subcategories. Then we have the name, the year-month app, which I believe is an identifier used by the city. The event start and end dates. The park, some events don't have one. Neighborhood, council district, precinct, the organization holding the event, and the estimated attendance. So what are we going to do with this data? Well, let's build a machine learning model. So since this talk is mostly about the feature engineering part, I'll just use a very simple model. We'll predict the binary outcome. Is the permit status complete or not? So did the event actually happen, or did it get canceled or put on hold for some reason? And for features, we can use any of the other columns. We can use them directly, apply various transformations, or maybe even use combinations, such as the start and end date together would tell us the length of the event. So we use scikit-learn to do our predictive modeling. And the first step is to split apart your test and training data. And then set aside your test data and don't look at it until the end. This way, through the training process, we don't have to worry about contamination. And when we finally see the test data at the end, we'll know how the model performs on brand new data. So then we'll define the outcome using the NumPy where function. And this just turns the permit status, whether it's complete or not, into a 0, 1 column. And then because this is a very simple model to start out with, we'll use the one numeric feature in the data set, which is the attendance. And just in case there are any null values, we'll fill those in with zeros for now. Then finally, we create our model object. I'll just use the logistic regression class with the out-of-the-box settings, so no parameters needed. Fit the model on the training data, and we can form predictions. So the predict function will produce a class, 0 or 1. And the predict proba will produce a probability. Actually, it produces probability of 0 and probability of 1, so we'll just grab the second column. We can also predict on the test data. All right, and this will help us evaluate how well the model performs. We'll start with it's always good to have a baseline. If we just come up with the dumbest model we can think of, how well would that perform? So the simplest model would be, let's just predict the average for everything. And then took the mean from the training data, and we just repeat that as many times as the length of the test data set. And then, of course, using the predict proba function to get the outcomes for the test data. And then we can evaluate using AUC. There are lots of other evaluation metrics, but this is the one I chose. So the baseline has an AUC of 0.5, and the very simple one-variable model has an AUC of 0.58. The maximum possible is 1. So it's not a great model, but for very little effort, we've certainly got something better than baseline. All right, so now let's move on to transformers. We had a one-variable model. Logistic regression wants all the features to be numeric. So if we didn't have the ability to do any transformations, we'd basically be stuck there. Luckily, scikit-learn provides a whole bunch of transformers as well as estimators. So these are two very similar interfaces scikit-learn has. A transformer is for data preparation, and an estimator is for modeling. They both have a fit method. And what this does is it takes the training data and finds all the parameters that the transformer estimator needs to use in the future. And sometimes transformers don't need any parameters. And then the transformer has a transform method, unsurprisingly. And this applies the transformation to either the training data or test data or any new data set you want. And the estimator in parallel has the predict method, which applies the predictive model to the test or training data. So for example, one common transformation you might want to do is the standard scalar. In the fit method, it will find the mean and standard deviation of each column from the training data. And it saves these values. And whenever you call transform, it subtracts that mean and then divides by that standard deviation on the new column. What's great about the standard scalar is it puts all of your features on the same scale, which means, say if you're fitting a regression model, you can interpret the coefficients to be related to the strength of the feature contributing to the model. On the other side, we have an estimator, logistic regression. So we already took a look at this one. In the fit method, we just find all those coefficients in the logistic regression formula, so all those betas. And in the predict method, we plug in the new data into that logistic regression formula, and we get the predicted probability, turn that into the predicted class. All right. Well, sometimes you want to go through multiple transformations in the course of feature engineering. So say first we want to impute the missing values, and for that there's a built-in imputer class. Then maybe we want to throw in some interactions and square the variable. So by default, the polynomial features class will just do the second degree polynomials. And then finally, the standard scalar at the end. Well, by the time you've added 3 different transformers, it can get a bit clunky. So what if we had to put all these intermediate data sets through the transformers. Then we have to remember the order to apply them to the test data. This would be a pain. So luckily, scikit-learn has pipelines. Pipelines work as a meta-transformer where they'll take your whole list of transformers and apply them in a row. And this is how it works. So the pipeline takes a list. In this case, we have tuples of the transformer alias, and that can be whatever you want, and then the actual transformer object. And it will apply these in order. I have to call out, a lot of this talk was inspired by the Zach Stewart blog post that I linked to here. So, and then all we have to do is this. We can call fit transform on the training data, which will apply the fit to fit the transformer and then apply the transformation. And then we can call transform on the test data. And this is much simpler to write. But sometimes we don't just want to apply transformations in order. Sometimes we want to apply them in parallel. This is not like parallel computation, but say we can't decide which imputation strategy to use. Should we impute with the mean, the median, or the most frequent value? Well, let's just let our machine learning algorithm choose for us. So the feature union will put the results of these three transformers next to each other, so you end up with a wider data set. And it takes a list of the transformers in tuples with their aliases. And you could just write this: fit transform on the training data, transform on the test data. All right, so back to the data set. So let's take a look at that park column. So remember I called out most of the first, at least the head, didn't have parks. And the entire training data set has almost 400 rows, and over 350 of them are nulls. So I'm using the value counts function here from Pandas. And then some of the most common parks to have events in include Magnuson, Gasworks, Occidental, Green Lake. So we've got maybe 40 rows that have a park. But Seattle has over 400 parks. So there's a pretty good chance that our test data is going to have some parks in it that we've never seen before. And it's important that our transformer know how to handle that gracefully. Another interesting column is the attendance. So this is the one I used before. So I filled in the nulls with zeros. Let's see how many times I did that. So just call is null on the Pandas series, and that will produce a Boolean. Just sum them up. It happened to be 3 nulls. So I guess most of the time people estimate their attendance. And then you can use the plot function to take a look at the distribution. So here's the distribution of attendance on the raw scale. The danger with having this as a input feature is the events with those really high attendance, apparently goes up to 200,000, potentially can have high influence over your model because they're so far away from the other data points. If these have an unusual value, the predictions could get pulled towards it. So here it is on the log scale. This looks much closer to normal, and this is probably a better feature to use. So now we've got a bunch of different transformers in our toolkit. Let's see what we want to do. What if the transformation you want to do is not implemented? You've scoured the scikit-learn documentation, you can't find it. Well, one thing to check is, can you use the function transformer? So this is a generic transformer that scikit-learn provides, and you can just give it a function, and it will apply that function to the whole data set. So for example, we want to use this log 1p, which adds 1 to your x variable and then logs it. So it means that the zeros won't result in negative infinity values. So all you have to do is create a function transformer object, pass in that function, and then you can call transform with it. Or you can write your own custom transformer. So this is a very simple example. Obviously, we just did it with a function transformer. You don't need to, but just to start out. So we'll create a class called log1p transformer, and it will inherit from the transformer mixin. So the transformer mixin will take the fit and transform methods and automatically create the fit underscore transform method, which is just a convenience method. The fit method doesn't need to do anything because there aren't any parameters that the transformer needs to know from the training data. But the transform method, all it does is call the function on your data set and return it. So super simple, but this lays out the structure. But what are we going to do about that park column? So the idea is to use one-hot encoding. This is also called dummy encoding. The idea is instead of having a single column with a bunch of strings in it, we make one column for Gasworks with a flag, a 0, 1, one column for Magnuson, one column for each of the parks that we see in the training data. And there's a great built-in transformer that does this called the dict vectorizer. But the dict vectorizer doesn't have the input and output we want. So we'll create a class and create a field to hold that internal transformer. And I'll call this the dummy transformer. And we take the X data, which will be a bunch of string columns, and turn each of those into, each row of that data set into a record, a mapping from the column name to the column value. This is the format the dict vectorizer wants, so we fit it, and then we return the transformer object. In the transform method, we again turn our data set into records, dictionary records, and then call the transform on that internal transformer, go grab the feature names that it produces. So this will say, like, event park location equals Magnuson, event park location equals Gasworks. And pull the index from the original data set and just throw those back on and turn it back into a data frame. So, all right, so I've hinted at the complication of using pandas and pipelines together. But I'll dig a little bit more into it. So pandas data frames support many data types, whereas scikit-learn models usually expect all the features be numeric. Pandas data frames allow for missing data, but most scikit-learn models can't handle nulls. And finally, pandas data frames have labeled rows and columns, which is really useful when you want to interpret your model. If it says, oh, feature 42 is really important, great, what the heck is feature 42? Scikit-learn models will downcast, and transformers will downcast to NumPy arrays, which strip out these labels. So we really want to put those back on. So unsurprisingly, the solution is custom transformers. And the key here is pipelines are already pandas friendly, meaning they will take a data frame and return a data frame if all of its component transformers are. So we just have to write a bunch of custom transformers that return data frames, and then we can stay in pandas land for the whole machine learning process. So there are a few different reasons we might want to write the custom transformers. Maybe we just want to pull out the columns that we want to work with, wrap existing transformers to reapply those labels, or some more complex logic. Say the transformer you want really is not implemented. Well, you can go implement it yourself. All right, so here's the column extractor. So all this does is pull out the columns we want to work with, and this is very useful for future portions of pipelines. So the fit method doesn't do anything. The initializer, we just give it the list of columns we want, and the transform takes the pandas data frame and slices to those columns. And here's the standard scaler. So the standard scaler is one of those transformers that returns NumPy array. So we'll just wrap it with a custom transformer. We'll create a field for that standard scaler to live in. For the fit method, we'll just fit it and save it. And then for the transform method, we'll transform with that internal standard scaler and then put the index and the column names back on. Great, so now let's put it all together and fit a more complex predictive model. So I'll make a list of the categorical features. We've got the permit type, the event category and subcategory, the park, and the neighborhood. And then the numeric features, well, the only one was attendance. So now we'll create our feature engineering pipeline. So this pipeline has two components. It has the features, which is a data frame friendly feature union, and the code for that is in the GitHub repo. And the second element is this standard scaler. And then inside that feature union, we have the categorical pipeline and the numeric pipeline. In the categorical pipeline, first we extract the columns, and then we apply that dummy transformer. In the numeric pipeline, we extract the columns, we apply this zero fill transformer, which I also wrote, and then apply the log1p. So now that we have that the whole transformation process wrapped up in that pipeline, we can apply it to the training data, just transform the test data with it, and use a logistic regression again, fit the model, predict on the test data, and our AUC has gone up from 0.58 to 0.71. So pulling in all those extra features helped. And that's all I've got. So here's a link to my GitHub repo. If you're interested, there are a whole variety of additional transformers. And I also have examples of transforming almost all the features in the data set. We are only able to touch on a few. Happy to take questions.
So thank Julie for
How long did I take? Oh, I went really fast.
So, well, everyone in the room tweets any questions you might have, including on the live stream. The question I want to lead off with is, do you have any recommendations or anything to deal with potential performance bottlenecks or issues you might typically run into when doing this that people should probably be aware of when they start with this so they don't get bogged down in trying to deal with some slow model or anything?
Yeah, so the idea here would be implement your transformer the simplest way first, and then if that's slow, try to go in and optimize it. It will just depend on your data set. I got mine fast enough that I could use them for the model I was working on, and I stopped there. But before putting this into open source, some official version, you should definitely go through and make it optimized.
Okay. Another question I had was, one of the jokes in the earlier openings keynote was about Pandas's API not being widely loved.
Mm-hmm.
Do you have any guidelines or anything on how to kind of work around it or deal with it if you happen to be bumping up against it and having some issues working with it, by any chance?
Yeah, so Pandas has a variety of different ways to access the columns, and sometimes one works and another doesn't. So that's always fun. If you use this sort of structure of the pipeline, and you've already QA'd each of the individual components, then you know it's all going to work. Mm-hmm. I don't know, what other complaints do people have about Pandas? I really like having my columns labeled. I think that's super useful in evaluating how the model is performing, trying to understand what the most important features are, and so on, especially when you introduce new features or you filter out other ones.
So one question we did get from the audience is for custom transformers that input data frames, output data frames, what is the memory usage typically? And is it copied back and forth, or are they using references?
Okay, so the transformation method is going to be whatever you write. I imagine it is copying, but you could probably write a more efficient one if you wanted.
Okay. That question was just asked. Were there any questions from the audience specifically that we can repeat? Yes.
To sort of build on that last one, is it possible to adapt this to a situation where you have a data set that will not fit in memory? It has to be streamlined?
So the question was, if you have a data set as like an example now that is too big to fit in memory and would need to be streamed, how would you handle that?
Well, I personally haven't worked with a lot of streaming data sets, but so the pipeline's pretty flexible. If you can wrap, maybe you don't want to be transforming Pandas data frames. Maybe you want to be transforming some sort of streaming object. And so I imagine you could put that into a pipeline instead and use the same sort of structure.
Yes. Rather repeat the question better than I can.
Okay, the question was, why would you use a dummy transformer instead of a regression tree method? So can you explain to me what you would do with the regression tree?
So just handling categorical variables for what you're trying to predict. So like, you have red versus blue, and you're trying to do just regression.
Right, so the idea with the one-hot encoding was that I want to put these into, say, well, my example was a logistic regression with a lot of other features. In that case, it does want the numeric encoding. People have asked me, why will you use this form of one-hot encoding instead of one of the built-in ones? So I have a couple slides if you're interested. I don't know. Sure, we have lots of time because I went faster than I was expecting. All right, so Pandas has a get dummies. This will work on a single data set, but it's not really good for applying it to a new data set. Scikit-learn preprocessing has a label encoder and a one-hot encoder, but both of using these together, it arrows out if there are new levels in the data set, in the test data. And then finally, the dict vectorizer, I ended up having to wrap with the transformations on each end to get the data in the right format. But that was the one that worked best for me. So.
One question we had from Twitter was talking about how you handle unseen categories with one-hot encoding in your test data.
Yeah, so what I did is basically give them all zeros, but there are other options. So if, you could use a feature hasher instead of a one-hot encoder. So what that will do is put all of your features into bins. So hopefully the really common ones will end up in different bins from each other. It's a good high-dimensional approximation of one-hot encoding, and then you don't have an explosion of your data set size. The other thing you can do is you can create one more column to indicate whether the value, say the park, was NA versus a new value.
Another question we got was, how do you decide on the number of engineered features you want and not get too many in the end?
All right, so I like to start with as many features as possible and then let my machine learning algorithm try to whittle it down. And in fact, in the extended code on the GitHub where I transform it, almost all of the columns, the performance starts degrading. I think it's a 0.69 AUC. And so at that point, we're already starting to overfit. You could add a higher penalty to the logistic regression to whittle down the number of features. I would say, put in as much time as you feel like into the feature engineering and see how it does and sort of iterate back and forth to the point where you're happy with your model.
Were there any other questions from the audience? Yes.
Have you put a pipeline, a scikit pipeline in production? And if you did, how did you do it?
So the question was, has Julie ever put a scikit-learn pipeline into production, and if so, how?
All right, so so one way to do this would be to save your transformer object and sort of keep it running in Python. I think you can serialize them depending on what the inputs are. Anyhow, so you could. It's pretty easy to spin up a pipeline, and you can then put that on some instance in the cloud and use that as your scorer. You could put an API in front of it and score that way. Another way to use this is just to write down your resultant model and all the transformations that you ended up needing to have at the end. As I said, you throw in as many features as I can and then whittle it down and just translate it into another language. So.
Right. Yes.
Are there any plans on releasing your wrappers as a package?
So the question was, does Julie have any plans to take her wrappers and release it as an independent package?
I haven't thought about that far yet, but it is all on GitHub, and you're free to download them. So the way I usually do this is I put all the custom transformers in a separate file, and then I import whichever ones I want to use.
Yes.
Talk a little bit about how the dummy transformer helps to basically handle if a part shows up in the test set and the training set.
Right. Okay. So.
Can you repeat the question?
So the question was again about the dummy transformer. If I flip back to that. Oh, too far. Okay, so in the dummy transformer, what it does is it creates a flag column for each of the parks that would show up in the in the training data. And so when a new value comes along, all the dict vectorizer is going to do is say, I've never heard of this value. You get zeros for each of those flag columns. So depending on if you do have NAs, the dict vectorizer will create another column that indicates whether the original column was NA or not. And there are two ways to handle that. You can either drop it or you can turn it into a flag. Originally, it's encoded as a 0 NA, which is not useful because we don't want nulls. But you can turn it into a 0, 1. Did you?
Is that applied through both the testing and the training?
Yeah, so the training data is not going to have this scenario happen where it's an unknown park because you built the transformer on the training data. But when you apply it to a new data set, it will have to know how to handle those new values that come in and just not error out. There are other options for handling it. You need something that your program doesn't crash.
Okay, well, as you can probably see out the window, it's time for lunch. So let's thank Julie one more time for giving the talk.